When a diode is, look, listen to me, when a diode is reverse bias, right? No current flows through the diode. That's what normally we that's how we tell it, right? Normally, no current flows through diode. Why do you use the term normally? When a diode is reverse bias, no current flows through it normally. What is the meaning of normally? The meaning of normally is this here, right? I think you are able to see the screen clearly. There are free electrons in the N semiconductor side. There are free electrons in the N semiconductor side. You see, there are free electrons in the N semiconductor side. Right? And similarly, there are holes in the P semiconductor side. Right? That's it. But you should know that there are some holes in the P semiconductor side. How those holes are generated, dear Lamai? How those holes are generated? I have asked the mechanism of generating of holes. Yeah, there are bonds between the silicon atoms. We know that. We know that there are silicon atoms, right? And there are covalent bonds between the silicon atoms. So if we consider two silicon atoms, look at board carefully. If we consider two silicon atoms, there is a covalent bond between them, right? So let us consider this silicon atom and another silicon atom, which is it is possible to be these two silicon atom anywhere in the diode, right? So we know that they make bonds. These silicon atoms make bonds like this. Got it? So because of these bonds, right, it is possible to break this kind of bonds. Right? So in each such bond, there are electrons. There are two electrons. There will be an electron here, right? And there will be another electron here, right? So one electron is given by one silicon atom. The other electron is given by the other silicon atom, right? So due to the heat energy, due to the rising temperature of the piece of this silicon, it is possible to break this bond. It is possible to break this bond. So once this bond is broken, this electron leaves the bond, right? Once an bond is broken, the electron leaves the bond. The electron leaves the bond, right? So when an electron leaves the bond, what will happen to the bond here? What will be created? What is the thing which is created in the bond here? Lamai?
A hole is created.
A hole is created, which is known as the vacancy for an electron is created. A vacancy for an electron is created in the hole, in the covalent bond. So therefore, when a bond between any two silicon atoms is broken, when a covalent bond is broken between any two silicon atoms, holes and free electrons are generated, right? So let me draw free electron which is generated by due to broken of a hole, broken of a covalent bond, right? So there will only be very few number of free electrons which are created due to the broken covalent bonds, but still there are some, at least very few free electrons are there. But majority of the charge carriers, the major one, the larger number of holes will be there in the p semiconductor. So therefore, for a p semiconductor, holes are known as majority charge carriers. Majority charge carriers or current carriers. Got it, dear? So who are the majority current charge carriers, dear? Lamai? In a p semiconductor, who are the majority charge carriers?
Holes, sir.
Holes. But in addition to these holes, there are some free electrons. There are some free electrons. They are known as, what's the name that we use for them, dear? What's the name that we use for these thermally generated free electrons, dear? Lamai?
Charge carriers.
Minority charge carriers. They are known as minority charge carriers. Minority charge carriers. Okay, dear? Right. So here we have said that no current flows through the diode. Means not there is no considerable current. No considerable current. And no current is created in the diode due to the majority charge carriers. Can you understand it? Lamai?
Yes, sir.
Right. And if there is an electron or a hole reaches to the depletion layer, electrons are pushed toward the N semiconductor, holes are pushed towards the P semiconductor. Right. My question is, listen to me carefully. What will happen if this electron reach to the depletion layer? Then what will happen? Lamai? If this electron reach to the depletion layer, then what will happen?
It will get pushed back.
Pushed. What is the force formed on this electron, dear? I have marked.
Oh.
Huh?
Wait.
What is
It
the
will be-
direction of the force given by the supply voltage Fs? P to N or N to P. This is the P semiconductor. This is the N semiconductor side. So to which direction the force is formed here?
P to N.
P to N. Therefore, what will be the moving direction of this electron here?
P to N.
P to N. So it means the electron will not be moved back to the P semiconductor side. It will be moved to the N semiconductor side. Actually, it will flow, it will move until it meets the positive terminal of the battery. Until it meets the positive terminal of the battery. Is it clear or not? Lamai?
Yes, sir.
Clear. Give me a minute, Kuta, 1 minute. Okay, sorry for the late. Right. So I have asked you about this electron which is generated thermally due to the rising temperature. It is possible to break covalent bonds between silicon atoms, and it is possible to create electrons and holes. So these are thermally generated holes which are known as minority charge carriers, because there are only very few free electrons like this. So once a free electron reaches to the depletion layer, the supply voltage force Fs and the junction force Fi both are acting towards the N direction, N semiconductor side. So it will be moved from junction to the positive terminal of the battery. So even, listen here, even if you consider, right, even if you consider this electron, even if you consider the electron when it is in this P semiconductor side, right? So this is the negative terminal of the battery. Can you see? Negative terminal of the battery, negative electron. So negative, negative, will they attract or repel here?
Repel, sir.
Hmm?
Repel.
They repel. Then dear, then what is the direction of force formed on it there?
Right hand side.
The direction of the force is into the right hand side direction. So let me mark it as Fs. So Fs force is directed to the N semiconductor side. So because of this force, because of this Fs force, the electron is moved to the junction. Once it reaches to the junction, both Fi, the junction electric field force, and the Fs, supply voltage force, they both of them push the electron further towards the N semiconductor side. It means the minority charge carriers, electrons in the P semiconductor, they move from P to N. Am I right, Lamai?
Yes, sir.
Right. So because of the minority charge carriers, if electrons move to one direction, what is the direction of the current there? Lamai?
Opposite direction.
Opposite direction. So it means what is the direction of the current? The opposite means
Opposite to the direction of the electrons.
yeah, it means electrons move from P to N. Therefore, what should be the direction of the current?
N to P.
N to P. Right. So please write a subheading. Please write today's subheading: leakage current and breakdown. Leakage current and breakdown of a reverse bias diode. Leakage current and breakdown of a reverse biased diode. Got it? Lamai?
Yes, sir.
Right. Under that, please write when a diode is reverse biased. When a diode is reverse biased. When a diode is reverse biased, comma, no current flows through the diode. No current flows through the diode due to the majority charge carriers. Due to the majority charge carriers. No current flows to the diode due to the majority charge carriers. When a diode is reverse biased, no current flows to the diode due to the majority charge carriers. Full stop. But there will be a very small current through the diode, but there will be a very small current through the diode due to the minority charge carriers. Due to the minority charge carriers. Due to the minority charge carriers. Full stop. That small current is known as that small current is known as it's a different color pen and write. It's a different color pen and write. Minority charge, leakage current. That small current is known as leakage current. Use a different color pen and write. That small current is known as, a different color pen and write, leakage current. Okay, dear Lamai?
Okay, sir.
Right. Within brackets, please write normal color within brackets. Free electrons which are generated by broken covalent bonds. Free electrons which are generated by broken covalent bonds, comma, are known as minority charge carriers in p semiconductor site. Free electrons which are generated by broken covalent bonds, are known as minority charge carriers in p semiconductor site. Do not close the bracket. Still keep the bracket open. Free electrons which are generated by broken covalent bonds are known as minority charge carriers in p semiconductor site. Okay, dear Lamai?
Okay, sir.
Continue. Similarly, holes, the holes which are generated by broken covalent bonds, are known as similarly, the holes which are generated by broken covalent bonds are known as, it's a different color pen and write, minority charge carriers, in minority charge carriers in N semiconductor site. Minority charge carriers in N semiconductor site. Okay, dear. Am I?
Okay, sir.
Right. Somebody unmute the mic and read the entire note that I have given today. Somebody unmute the mic and read the complete note that I have given today.
When a diode is reverse biased, no current flows through the diode due to the majority charge carriers, but there will be a very small current through the diode due to the minority charge carriers. That small current is known as leakage current, in brackets, free electrons which are generated by broken covalent bonds are known as minority charge carriers in p semiconductor side. Similarly, the holes which are generated by broken covalent bonds are known as minority charge carriers in N semiconductor side.
Right. Thank you, dear. Thank you very much. Thank you very much. One more students, please unmute the mic and read the entire note that I have given today. One more student.
When a diode is reverse biased, no current flow through the diode due to the majority charge carriers, but there will be a very small current through the diode due to the minority charge carriers. The small current is known as leakage current. Within open bracket, free electrons which are generated by broken covalent bonds are known as minority charge carriers in p semiconductor site. Similarly, holes which are generated by broken covalent bonds are known as minority charge carriers in N semiconductor site.
Thank you, dear. Thank you very much. So, please draw, wait, star point and write. Star point and write. Forces are formed on the minority charge carriers. Forces are formed on the minority charge carriers. Forces are formed on the minority charge carriers within brackets electrons. Forces are formed on the minority charge carriers within brackets electrons. Within brackets electrons in the N semiconductor side, in the P 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 semiconductor side, directed from P to N, directed from P to N, directed from P to N, within brackets, look at board and write within brackets, Fs, within brackets, please write Fs, full stop. Due to that forces, electrons are moved. Due to those forces, electrons are moved. Due to those forces, electrons are moved from P semiconductor side to the N semiconductor side. Electrons are moved from P semiconductor side to the N semiconductor side through the junction. Through the junction. Through the junction. Through the junction. As if full stop continue, as electrons are negative charges. 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 The current is created. The current is created into the opposite direction. The current is created into the opposite direction. Within brackets, N to P, N to P. The current is created into the opposite direction within brackets N to P. N to P. Full stop. That current is known as, leakage current. That current is known as leakage current. Okay, dear? Lamai?
Sir, could you repeat the last sentence, please?
Yeah. That current is known as leakage current. Can somebody read the that part completely? Somebody please unmute the mic and read that part completely.
Forces are formed on the minority charge carriers within bracket electrons in the p semiconductor side directed from P to N within bracket Fs. Due to those forces, electrons are moved from p semiconductor side to N semiconductor side through the junction. As electrons are negative charges, the current is created into the opposite direction within bracket N to P. That current is known as leakage current.
Did you complete the note, dear? Would like if somebody read the note again, once again? Anybody in the class? Yeah, somebody unmute the mic and read the entire note once again. Somebody unmute the mic and read the entire note once again. From the very beginning, dear.
When a diode is reverse biased, no current flows through the diode due to the majority charge carriers. But there will be a very small current through the diode due to the minority charge carriers. That small current is known as leakage current. Within brackets, free electrons which are generated by broken covalent bonds are known as minority charge carriers in p semiconductor side. Similarly, the holes which are generated by broken covalent bonds are known as minority charge carriers in N semiconductor side. Forces are formed on the minority charge carriers within brackets electrons in the p semiconductor side directed from P to N within brackets Fs. Due to those forces, electrons are moved from the p semiconductor to the N semiconductor side through the junction. As electrons are negative charges, the current is created into the opposite direction within brackets N to P. That current is known as leakage current.
Right. Thank you, dear. Now, please draw this figure. After that, I'll explain. Please draw this figure, dear, quick. If you have doubts while you are drawing the figures, you can ask me, right? I'm here. Lamai, somebody please unmute the mic and read the last few sentences of the note. Somebody unmute the mic and read the last few sentences of the note.
Due to these forces, electrons are moved from p semiconductor side to n semiconductor side through the junction. As electrons are negative charges, the current is created into the opposite direction within brackets n to p. That current is known as leakage current.
Thank you, dear. There is no anything. There is no mistake, right? Is there any mistake in that point?
No, sir.
It's clear, right? Right. The other thing that I want to explain is, please wait. Please stop for a while. Please stop. Please wait for a while. The other thing that I want to explain is, so you see this bond. When there are when there's a covalent bond between any two silicon atoms, there is a possibility to break. So what is this, dear? This is the free electron. So what is this one, dear? This one, Lamai?
Holes.
Hole. So electrons are the minority charge carriers. Minority charge carriers in p semiconductor side. If you consider n semiconductor side, holes are the minority charge carriers. So there is a possibility to be some holes in the p semiconductor side. Is it clear here? Lamai?
Yes, sir.
So what is the direction of the force formed on such a hole? This is the positive terminal. Holes can be treated as movable positive charges. So positive repel. Therefore, forces are formed on the holes directed from N to P. So these holes are pushed towards the N semiconductor side. So when such a hole reaches to the junction like this, what will happen there? Boron negative ions and positive hole attracted. Arsenic positive ions and positive hole repelled. So, and the negative terminal, you see negative terminal of the conductor connected to this side. So negative terminal attract this hole. So the total force acting on the hole is directed into the p semiconductor side. Therefore, this hole will be moved from N semiconductor side to the junction to the negative terminal of the battery, right? So it means holes in the N semiconductor side are moved to the P semiconductor side across the junction. Holes are positive charges. If positive charges move to one direction, what will be the direction of the current created by them? Lamai?
Into that direction, sir.
To the same direction. So therefore, due to these minority charge carriers, holes in the N semiconductor side, a current is created from N to P direction. Am I right, dear?
Yes, sir.
Right. Have I given that holes are minority charge carriers in the N semiconductor side, dear? Check whether I have given such a note. Lamai? Please tell me yes or no.
No,
I think,
sir.
as I remember, I have given that holes are the minority charge carriers in N semiconductor side. Have I given or not?
Yes, sir. Given.
So please mark this also. Please mark them also. Earlier I described only the electrons, but we should describe both. So the force given by the supply voltage Fs directed on the holes from P to N. So due to the Fs force, holes are moved from N semiconductor side to the P semiconductor side. That's what I want to tell you, right? So majority charge carriers moved away from the junction, but minority charge carriers, they go through the junction. So there will be a current through the junction due to the minority charge carriers, but the number of minority charge carriers very small, right? There are only very few number of minority charge carriers. Therefore, the current created by them will be very, very small. The very small current which is created by these minority charge carriers known as the leakage current. Is it clear for all, Lamai?
Yes, sir.
Pullaigal, is it clear? That's the Tamil term for Lamai. Pulla is the singular term, Pullaigal is the plural. Am I right, dear? Right. Complete the figure, dear. Quick. A student asked me a question like this. Let me read. Free electrons which are generated by broken covalent bonds are known as minority charge carriers in p semiconductor side. 100% correct. 100% correct. When we are in America, we are the minority. Am I right, dear? If we go to America and if we stay there, who are the minority nation, dear? We or Americans? Lamai? We are the minority if we go to America. Let's say some Americans come to Sri Lanka and stay here. Then who are the minority? We or Americans when they are in Sri Lanka?
Americans, sir.
Americans. So minority depends on the place where they live. So there is no upset in this sentence. Let me read here. So therefore, holes, electrons are the minority when they are in p semiconductor. Holes are the majority. If holes come to n semiconductor, in an n semiconductor side, holes are minority, electrons are majority. Is it clear? Clear? Minority majority changes according to the place. Okay. අපි ලංකාවේ ඉන්නකම් අපි තමයි පොරවල් අපි තමයි මැජොරිටි අපි කට්ටියම පන්තින ළමයි නිසරි ඔක්කොම ඇමරිකා ගියොත් අපි මයිනොරිටි am I right dear ළමයි
Yes, sir.
ඉතින් අපි මැජොරිටි විදිහට ඉන්න ආස නම් ලංකාවටලා ඉන්නවා ඔයාලා කල්පනා කරනවා මයිනොරිටි උනත් කමන්නේ ඇමරිකාවට යන එක තමයි හොඳ කියලා ආ එහෙම නම් හිට යන්න පුළුවන් තේරුණාද කියන දේ
Yes, sir.
හැබැයි ඇමරිකාවේ ගිහිල්ලා අපි කිව්වොත් නෑ නෑ ලංකාව තමයි හොඳම රට පිස්සු කතා කරන්න එපා සුද්ධෝ එහෙමද කියලා කන්ට එකක් ගහලා හපවෙයි ඈ ඊටපු දැන් නොප්පලයව කියලා Right. Is the time enough for you to draw the figure here? Who wants any more time to draw the figure? Right, somebody unmute the mic and read the complete note before we go to the next part. Somebody unmute the mic and read the complete note.
When a diode is reverse biased, no current flow through the diode due to the majority charge carriers, but there will be a very small current through the diode due to the minority charge carriers. That small current is known as leakage current. Open bracket. Free electrons which are generated by broken covalent bonds are known as minority charge carriers in p semiconductor side. Similarly, holes which are generated by broken covalent bonds are known as minority charge carriers in n semiconductor site. Close bracket. Forces are formed on the minority charge carriers within bracket electrons in the p semiconductor site directed from p to n within bracket fs. Due to those forces, electrons are moved from p semiconductor site to n semiconductor site through the junction. As electrons are negative charges, the the current is created into the opposite direction within bracket n to p. That current is known as leakage current.
Right. One more star point and right. One more star point and right. Similarly, the minority charge carriers. Similarly, the minority charge carriers within brackets holes. Similarly, the minority charge carriers. Similarly, the minority charge carriers within brackets holes in the n semiconductor site. In the n semiconductor site are moved from N to P, are moved from N to P across the junction, are moved from N to P across the junction due to the forces formed on them. Due to the forces formed on them. Due to the forces formed on them. Full stop. As holes are positive charges, 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 the direction of the current created by them. As holes are positive charges, the direction of the current created by them, the direction of the current created by them is N to P. Direction of the current created by them is N to P. N to P. N to P. Therefore, a leakage current is formed across the junction through the diode. A leakage current is formed through the diode. A leakage current is formed through the diode, even due to the holes. Even due to the holes in the n semiconductor site. Even due to the holes in the n semiconductor site. Okay, dear. Lamai.
Yes, sir.
Right. Somebody please read that point also.
Similarly, the minority charge carriers within bracket holes in the n semiconductor site are moved from N to P across the junction due to the forces formed on them. As holes are positive charges, the direction of the current created by them is N to P. Therefore, a leakage current is formed through the diode even due to the holes in the n semiconductor site.
Thank you, dear. Thank you very much. Star point and right. The number of minority charge carriers, the number of minority charge carriers, comma, is very small and the number of minority charge carriers is very small and constant. It means there may be 10 number of minority charge carriers and they constant. The number of minority charge carriers, comma, is very small and constant. Therefore, they create a current, they create a constant, very small current. Therefore, they create a very small constant current. Therefore, they create a very small constant current. The number of minority charge carriers, comma, is very small. Full stop. Therefore, they create a very small constant current. A very small constant current. Okay, dear. We'll stop and continue to the same point. Therefore, the variation of the current with the supply voltage. Therefore, the variation of the current with the supply voltage will be as shown in the following graph. Therefore, the variation of the current with the supply voltage will be as shown in the following graph. Okay, dear. Even last week we have learned something so called a VI characteristic. Do you remember it? Lamai? Hello? Can you hear me?
Yes, sir.
Ah, yes. Did you remember that we have drawn VI characteristic?
Yes, sir.
Yes. I don't ask you to draw. Don't worry. Don't be so much afraid. Right. Right. So here we know that what is the equation of the current here? Any current is equal. Normally we write Q equals IT. Right. From this we can subject I. So I equals Q divided by T. So Q is the amount of charge flows to a certain circuit. Right. Q is the amount of charges flows to a certain circuit. Right. So here the charges are the minority charge carriers. So we have very small number of minority charge carriers. So therefore, when Q is small, current should also be small. Q is the amount of charge flows through the circuit. So charge mean minority charge carriers. They are very small. There is a very small number of minority charge carriers. Therefore, current flows through the circuit should be small because charge is small. Got it, dear? Lamai?
Yes, sir.
Right. So therefore, what will be the graph? What will be the shape of the graph which shows the variation of the current with the voltage? That's what we are going to learn now. Right? I should erase these things because I want some space to draw. Right. So if I try to draw a graph between the supply voltage, please don't draw it, supply voltage VS and the current flows through the circuit. Now, dear, the direction of this supply voltage is reversed. If you check the circuit that we have drawn earlier and this circuit, the direction of the supply voltage was changed, right? So if one direction is taken as the positive direction for the voltage, the opposite direction should be, Lamai? If one direction is taken as positive for the supply voltage, what about the opposite direction, dear? What is it again?
Negative.
Right. So earlier we have taken, if you check in the previous connection, positive terminal connected to P side, negative terminal connected to N side. Now we have changed the direction of the supply volt. So if I take the direction, earlier direction as positive direction for the supply voltage, the new direction of the supply voltage should be negative, right? That's one of the points you should remember. So therefore, as the supply voltage is negative now, according to the direction, we should draw the graph in the negative side. We should select the negative side of the graph, negative side of the voltage. So if we draw this graph, initially there will be a very small increase in the current. If you check this one, there will be a very small, negligibly small increase in current at the beginning, like this. But if we increase the voltage further, this current will be a constant. Initially, there will be a very small increase, but with the time, this will be constant. So the negative means only the direction. Earlier direction was positive, therefore this direction is negative. But nothing is negative. Voltage is not negative. Only the direction of the voltage has been changed. And the other thing, look at board carefully. And the other thing is, if we increase the supply voltage 1 volt, 2 volt, 3 volt, 4 volt, 5 volt, 6 volt, like that, current remains unchanged. But it is not possible for the current to be like this forever. Right? It is not possible for the current to be stay like this forever. Right? So at a certain supply voltage, diode is burned and a huge current flows to the diode. What will happen here? Is it possible for the current to be remains unchanged like this forever, Lamai?
No, sir.
No, that is not possible. So when we increase the supply voltage, right? Let me use some dotted lines. It may be stay like this, but at a certain supply voltage, diode is burnt and a huge current flows to the diode. The voltage, the supply voltage at that time is said to be the breakdown voltage. Breakdown voltage, which is indicated by VB. So what is VB, dear? Breakdown voltage. So you should remember it, right? So if the supply voltage becomes greater than the breakdown voltage, a diode will be burned, right? And the other thing is this small current is in the microampere range. So if you connect a normal milliammeter, the reading of the milliammeter will be 0 when it is reverse biased, because this leakage current is a very, very small one. Is everything clear, Lamai? Hello?
Yes, sir.
Right. Draw this graph, dear. In the exam, they will ask you to draw this graph, okay? And you have to explain this VB voltage also. If you have any doubt, you can ask. Right. Did you draw the graph there, Lamai?
Yes.
Right. Put a star point and write. Star point and write. When the supply voltage is increased, when the supply voltage is increased, comma, when the supply voltage is increased, comma, the leakage current remains unchanged. The leakage current remains unchanged. The supply voltage is increased, comma, the leakage current remains unchanged. But if the supply voltage is continuously increased, but if the supply voltage is continuously increased, but if the supply voltage is continuously increased, comma, the diode is burned at a certain voltage. The diode is burned at a certain voltage, and the diode is burned at a certain voltage, and the diode is burned at a certain voltage, and a huge current flows through it. But if the supply voltage is continuously increased, comma, the diode is burned and a huge current flows through it. A huge current flows through it at a certain supply voltage. The diode is burned and a huge current flows through it at a certain supply voltage. We'll stop. That supply voltage is known as use a different color pen and write. That supply voltage is known as, use the different color and write, breakdown voltage. Breakdown voltage. Breakdown voltage. We'll stop. Once a diode is kept under the breakdown voltage, once a diode is kept under the breakdown voltage, once a diode is kept under the breakdown voltage, comma, it is completely damaged and it is completely damaged and it is completely damaged and it cannot be used after that. It cannot be used any further. It cannot be used any further. Okay, dear Lamai. Did you write?
Yes, sir.
Right. Put a star point and use a completely different color pen. It's better if you have a different color pen. Star point and write with a different color pen. But there is a certain kind of diode. There is a certain kind of diode. Certain kind of diodes known as Zener diode. Known as Zener diode. but there's a certain kind of diode known as Zener diode, comma, which are able to work normally, even under the breakdown condition. Even under the breakdown voltage, which are able to work normally even under the breakdown voltage. Okay, dear. So they are special kind of diodes, Zener diodes, but we do not learn them now. We learn them when we learn alternative currents and full wave rectifiers, half wave rectifiers. Under that section, we learn about the Zener diodes, but now we don't learn about Zener diodes. Okay, dear Lamai, we know now. Today we learn only about the normal diodes. Lamai, are you okay?
Okay, sir.
Right. So please write your next subheading: complete VI characteristic. Complete VI characteristic of a diode. What's the next subheading there? Complete VI characteristic of a diode. Right. What is this graph there? This is the VI characteristic of a reverse bias diode. Last week we have drawn the VI characteristic of a forward bias diode. So what is the VI characteristic of a complete VI characteristic here? This is the VI characteristic of reverse bias diode. Last week we learned VI characteristic of forward bias diode. So what is the complete VI characteristic here? Complete VI characteristic means the combination of forward bias and reverse bias. So if I add the forward bias connection, to this, then it will become when I draw forward bias and reverse bias together like this, then it becomes a complete VI characteristic. So I think I can easily draw it like this. I don't draw a circle for a characteristic, right? I just want to, I don't have any other way to get a curve. That's why I'm using a circle, but there are no circular graphs. Right. Now combine these two and draw the complete VI characteristic. Start there, Lamai. You should draw a separate graph, right? Do not edit the previous one. You should draw a separate graph for the complete VI characteristic. Start. So this is the complete VI characteristic of a diode. Okay, dear. Lamai.
Okay, sir.
What is this? There's a special voltage here. Even I think I have described it even last week. What is this voltage, dear? The voltage at which we get a surge is even a very small current. The junction, this bend, this knee bend starts here. That voltage has a special name. What is it, dear? Normally we indicate it as VJ. What is it, dear?
Junction voltage.
Very good. Junction voltage. What is the value of junction voltage for a silicon diode? Lamai?
0.7 volts.
0.7 volt approximately, 0.7, 0.6. What is the junction voltage for a germanium diode there?
0.3 volts.
0.3 volt, very good, approximately 0.3. Sometimes in the examination they will give 0.2. So they will give 0.2, 0.3 voltage. So then you should identify that in the question. If it is said that junction voltage is 0.3 volt or 0.2 volt, it means it is a, what kind of a diode is it there? It's a germanium diode. 0.2, 0.3 junction voltage means a germanium diode. In the exam, they will give you a diode. It is saying that junction voltage is 0.6 volt or 0.7 volt. So what is the kind of the diode there?
Silicon.
Silicon diode.
The diode is made from silicon. It's a silicon diode. So that's how you identify by looking at this graph. By looking at this graph, and if we know the value of the junction voltage, we can determine whether the diode is silicon or whether the diode is made of germanium. Okay, dear. Once you complete draw the graph, please tell me. Then I'll go to the next section. Who wants more time to draw this graph, dear? Lamai? Right. I think time is enough. I'll erase everything and I'll go to the next theory part. Normally, we should discuss half wave rectification, full wave rectification, bridge circuits, Zener diodes with this. But normally, you should draw this graph separately. This is a new graph. Complete VI characteristic of a diode is a new graph. So if you didn't have enough time to draw the graph, it's better. The best thing is taking a screenshot and you can complete this at home, right? So normally we should discuss bridge circuits after this, but I have changed slightly the order. I'm not going to teach bridge circuits now. I'm going to start transistor because it is the most important section, transistors and op-amps, operational amplifiers. So I'm going to start that section. I'll teach bridge circuits once I complete those sections. Direct current generator and alternative current generators in magnetic field lesson. Once I complete direct current generators and alternative current generators in magnetic field, I'll teach about the bridge circuits. Then it will be easy for you to understand. So now let's start the transistor section. If you did not draw this new graph, this is a new graph, not the previous one. Take a screenshot. Because I'm going to erase everything. I'll erase everything. Please quickly take a screenshot. Right. I have erased everything. Now I'm going to start the next section, transistors. So I have erased everything and I have written our new subheading, transistors. Please write your next heading and underline it. Okay. Right. Please write by connecting three different kinds of semiconductors. By connecting three different kinds of semiconductors, comma, a transistor can be constructed. A transistor can be constructed by connecting three different kinds of semiconductors, comma, a transistor can be constructed. Even though said don't write, even we say three different semiconductors, actually we don't have three different semiconductors. Listen there, we have p semiconductors, right? Then we have n semiconductors, don't draw it, n semiconductor, right? Then we have pure silicon crystals, pure silicon semiconductors. But if you connect a pure silicon semiconductor, pure semiconductor known as intrinsic semiconductors, if we connect a pure semiconductor, there will not be a considerable amount of current. There should be electrons or holes. Then how do we arrange three different semiconductors to make a diode there? If it is a p semiconductor, there should be holes. Right? If it is a p semiconductor, there will be holes like this. I'm here for a transistor, I'm only interested in holes and free electrons. So how do you make three different semiconductors? Can you suggest me a method B? Somebody in the class? Lamai? For any transistor, I didn't ask the kind of the transistor. I want three different semiconductors. So what is this semiconductor here? What is this semiconductor? The type of the semiconductor that I have drawn here. These are holes. So therefore, what type of a semiconductor is this? This is a p semiconductor, right? Because there are holes. Listen to me carefully. There are holes. So therefore, it's a p semiconductor. No problem, right? Now, here let's say, right? This is a n semiconductor. So if it is a n semiconductor, there should be many free electrons. There will be many free electrons. Right? Electrons will be there. But what do I want there? I want another semiconductor, another kind of a semiconductor to make a transistor. So my question is how to obtain another kind of a semiconductor here. One is N, the other one is P. What's the third kind of the semiconductor, Lamai? Are you think there?
P semiconductor.
Sorry, dear.
P semiconductor.
N semiconductor.
There's a P semiconductor.
This is a p semiconductor. Holes are there, means this is a p semiconductor. Let me mark this. This is a p semiconductor. P semiconductor. Right? This is an n semiconductor. My question is how to make another semiconductor. I want to make a transistor. I want another kind of a semiconductor here. So how do I make one? That's my question. Think there should be something different. Should not be the same. This is a p semiconductor.
Should it have a depletion layer?
Yeah, once two semiconductors are connected, definitely a depletion layer is formed. Yeah, definitely. There definitely be a depletion layer. So this is the n semiconductor, right? So this is the n semiconductor. This is the p semiconductor. Once you connect them, just after you connect them, right? Just after you connect them, a depletion layer is formed, right? A depletion layer is definitely be formed between them, right? So what is the other way to make another semiconductor? There must be a difference, right? Let me help you. How many holes are there? Count and tell me. How many holes are there in the P semiconductor? Count and tell me, dear.
13.
13, sir.
13. Huh. So the number of electrons depends on the number of arsenic atoms that you added. Am I right, dear? So there are 13 free electrons. Mean how many arsenic atoms have we added there? There are 13, 13 holes, not arsenic. 13 holes mean there are 13 boron atoms added. Am I right, dear? You have to tell me at least yes or no. Right. The number of arsenic atoms or boron atoms added to a semiconductor is known as its doping level. It's doping levels. So look at this connection. I'll reduce the number of holes. Now how many holes are there? Count and tell me. How many holes are there? Lamai?
6, sir.
6. So then it is said doping level is 6. There are 6 holes. Now, so it means how many boron atoms are there in this semiconductor here? 6 holes mean
6 boron atoms, sir.
boron atoms. Now, look at board here. I'll take another P semiconductor. I'll take another P semiconductor, right? Like this. And now count and tell me the number of holes in this P semiconductor here. Lamai, how many holes are there?
12, sir.
12. So it means many boron atoms are added into this semiconductor. Am I right here?
Yes, sir.
So many boron atoms are added, therefore many holes are created, which is known as highly doped. How do we call it here? If there are many boron atoms are added, which is said to be, it is highly doped, DO. I think DOP. Can you hear it? Right now, both are P semiconductors. Both are P semiconductors. What is the difference between them? Lamai? Just looking at the figure and tell me, dear, what is the difference between the first P semiconductor and the second P semiconductor, dear?
So the first one is having less number of holes.
Very good, excellent. The first one has a very few number of holes. The second p semiconductor has larger number of holes. It means the doping level of the first p semiconductor and the doping level of the second p semiconductor are different. When the number of holes are changed, they work in different ways. Therefore, now we have 3 different p semiconductors. Is it clear or not? Lamai?
Okay, sir.
So how do we make 3 different semiconductors? In the examination, they will ask how to make 3 different semiconductors, dear. What's the method?
Different doping levels.
By change in the doping level. It means by change in the number of boron atoms and arsenic atoms added. Clear? So if we connect 3 different semiconductors like this, this arrangement is known as a transistor. Okay, dear? Lamai?
Okay, sir.
Right. Now, by looking at this diagram, there is another way to make a transistor. What is that method, dear? Here I have connect 2 p semiconductors to the ends of a n semiconductor. What is the other method, dear?
We can have a p semiconductor at the middle and have 2 n semiconductors, top and bottom.
Very good, excellent, dear. So that's why I always ask students to talk. If you know, you will talk without the fear. Very good. So the other method is we can connect 2 n semiconductors to the ends of a p semiconductor. Right. The star point and right. Before that, would somebody please read the note that don't draw this figure. Lamai, please don't draw this figure. Somebody unmute the mic and read the note that I have given under transistors from the very beginning.
By connecting 3 different types of semiconductors, a transistor can be constructed, sorry.
That's all, neither.
Yes, sir.
Right. Continue the note. Continue the note. By changing the number of foreign atoms. By changing the number of foreign atoms. By changing the number of foreign atoms. Within brackets, A is arsenic and boron. By changing the number of foreign atoms added into within brackets arsenic and boron, close the bracket, added into a pure semiconductor. Pure semiconductor within brackets intrinsic, within brackets pure semiconductor within brackets intrinsic semiconductor comma, I forgot the sentence. Could you somebody, when I type, I forget the things. Somebody please read that sentence from the beginning. I forgot it.
By changing the number of foreign atoms, arsenic and boron added into a pure semiconductor, intrinsic semiconductor, sir.
Right, close the bracket, intrinsic semiconductor, close the bracket. The number of holes and the number of free electrons, number of holes and number of free electrons in an unit volume, in an unit volume, in an unit volume, in an unit volume can be changed. Number of holes and free electrons in an unit volume can be changed. Can be changed. Full stop. That process is known as, that process is known as doping. That process is known as doping. Doping. Look at board and write. That process is known as doping. Okay, dear. Sorry, that's a mistake. That process is not 1P. That process is known as doping. Full stop. If more foreign element, if more foreign atoms are added, 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 it is said that doping level is high. Doping level is high. If more foreign atoms are added, it is said that the doping level is high. The doping level is high. Full stop. If few, full stop and continue. If few foreign atoms are added, if few, FEW, if few foreign atoms are added, if few foreign atoms are added, comma, it is said that the doping level is small. It is said that the doping level is small. Full stop. Full stop. Two different p semiconductors can be arranged. Two different p semiconductors can be arranged. Two different p semiconductors can be arranged by changing the doping level. Two p semiconductors can be arranged by changing the doping level. By changing the doping level. Full stop. Full stop. If such, full stop and continue. If such two different p semiconductors, if such two different p semiconductors are connected, if such two different p semiconductors are connected, to the ends of a n semiconductor, to the ends of a n semiconductor, to the ends of a n semiconductor, comma, to the ends of a n semiconductor, comma, look at board, look at board, look at board, PNP, simple letters, PNP, sorry, a PNP transistor, a PNP transistor can be constructed, can be made or can be constructed. A PNP transistor can be constructed. Okay, dear Lamai? Hello?
Yes.
Right. So what is this transistor? What is the name of this transistor, dear?
PNP transistor.
PNP transistor. Right. Now, I want to tell you something further, right? The semiconductor which is highly doped, the semiconductor which is highly doped is known as the emitter. That's the point here. You must have learned physics or electronic as a subject in university to know these things. So these two behave in different ways. So if you connect a metal wire, listen here, if you connect a metal wire to this P semiconductor and this P semiconductor, they are not identical. They are not same. So the semiconductor having lower number of holes or the slightly doped P semiconductor is known as collector terminal. What is that? What is the name of that terminal, dear? Collector terminal, right? The semiconductor, the metal, this is a metal wire connected to the highly doped is known as emitter. Emitter terminal. Got it, dear? That's how the names are given, dear. Right? Emitter mean having more number of holes, highly doped. What is the middle one? Everybody knows the name of the middle one. Lamai? What's the name of the middle terminal? Lamai?
Base.
Base. Everybody knows it. That is known as the base terminal. Draw this figure. Now draw this figure, dear. Now draw this figure. And name or everything. This is base terminal. Let's use capital B. Base terminal. So can you identify the doping terminals according to the doping levels now, dear? Lamai? You should be able to identify the doping level by looking at the names. Collector, slightly doped. Emitter, Lamai? Emitter,
Highly doped.
highly doped.
Hi.
So very good. So you should remember those things. Spelling's wrong, dear. Wait. Emitter spelling wrong. 1M and 2T. Okay. Collector correct. Right. Okay, dear. Draw this figure. I'll remove the unwanted things. We don't want this one, this, and this. Right. Now tell me how many depletion layers are formed. While you are drawing, please tell me the number of depletion layers formed here.
2, sir.
2. The first depletion layer is formed between
Collector terminal and the base.
Collector section and the base section. What is the second depletion layer?
Base and the emitter terminal, sir.
That is base section and the emitter section. So if you consider only the P section and N section, what is it there? If you consider this first one and second one, what is it there? You know the name. If you consider the P semiconductor section and this N semiconductor section, it has a name. What is it called here? If you connect the P semiconductor and N semiconductor together, what is it called? What is it there? Lamai?
PN junction.
It's a PN junction. So PN junction means what?
Junction diode.
It's a junction diode. Oh, very good. If you connect a P semiconductor and a N semiconductor together, you get a junction diode. So it means there is a junction diode between the first P section and next N section. Am I right here? Lamai?
Yes.
Then there is another diode between the P section, N semiconductor section and the second P semiconductor section. Am I right? Okay or not?
Okay, sir.
Right. So it means actually how many diodes are there? How many diodes are there?
2, sir.
There are 2 diodes. So it means actually in a transistor, right? You must have good idea, dear. You should be able to explain everything, right? If you have learned electronics in university level, then only a teacher is able to explain those things, dear, right? Otherwise, he or she can't explain. So actually, there are 2 diodes. Actually, there are 2 diodes. But are the 2 diodes similar or different?
They are different, sir.
They are different diodes. That's the point, right? So if you consider base terminal, and the collector terminal, right? There is a diode in it. There's a diode between them. If you consider base terminal and the collector terminal, there is a diode between them. I forgot to give you this circuit symbol of a diode. What is the, I think everybody knows it. Circuit symbol of a diode is there is an arrowhead like this. Don't draw it. Just don't draw it. There's an arrowhead like this, right? This arrowhead indicates the direction of the forward bias current through a diode. So what is the direction of the forward bias current of a diode? P to N or N to P? Lamai?
P to N.
Sorry?
P to N.
P to N. But what about my arrowhead here? Is it directed from P to N or N to P? This is base.
N to P, sir.
Base is base terminal is N. This is collector. Collector terminal is P. So what is the direction of the arrowhead that I have drawn here? N to P or P to N?
N to P, sir.
So is it correct or wrong?
Wrong.
Wrong. We should change the direction of the arrowhead. So in the circuit symbol of a diode, there should be an arrowhead. That arrowhead gives the direction of the current when a diode is forward biased. Okay, dear? So forward bias current flows from P to N. Therefore, arrowhead should be into here. Right. Now correct. Now is it correct or wrong, dear?
Correct.
Then what is this line, dear? This one. This line of the circuit symbol indicates the junction between P and N. There are 2 semiconductor layers, P and N. So this line indicates that line. Okay, dear? Lamai?
Okay, sir.
Right. I will give you more time to draw this figure. Don't worry. I will give you more time to draw this figure. Put a star point and write. Due to the connections of P semiconductor layers and the N semiconductor, due to the connections of P semiconductors and the N semiconductor comma, 2 different diodes are formed internally. 2 different diodes are formed internally. 2 different diodes are formed internally. Got it? Therefore, a transistor can be treated. A transistor can be treated. Therefore, a transistor can be treated as a combination of two different diodes. A transistor can be treated as a combination of two different diodes. Different word is very important. A transistor can be considered as a two different diodes. Full stop. Within brackets, please write. Within brackets, please write the arrowhead on the circuit symbol. The arrowhead on the circuit symbol of a diode within brackets. The arrowhead on the circuit symbol of a diode. The arrowhead on the circuit symbol of a diode indicates the arrowhead on the circuit symbol of a diode indicates the direction of the current, indicates the direction of the current when the diode is forward bias. When the diode is forward bias. When the diode is forward bias. Okay, dear. Lamai.
Okay, sir.
Would you
Okay,
please
sir.
read that note, dear? Please read that star point, dear.
Due to the connections of P semiconductor and the N semiconductor, two different diodes are formed internally. Therefore, a transistor can be treated as a combination of two different diodes. Open bracket. The arrowhead on the circuit symbol of a diode indicates the direction of the current when the diode is forward biased.
Next star point. Thank you, Buddha. Next star point. When a diode is forward biased, 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 comma, a current flows through it, a current flows through it from P to N. A current flows through it from P to N. A current flows through it from P to N direction. From P to N direction. When a diode is forward biased, a current flows through it from P to N direction. So look at what there. Therefore, what is should be the direction of the arrowhead of the diode between base and emitter here? Directed from emitter to base or base to emitter? Lamai? Again,
Emitter to base.
emitter to base, P to N. Emitter is P, base is N. So therefore, arrowhead of the diode between base and emitter should be directed from emitter to base. Emitter to base. Okay, dear. And now please draw this circuit also. So in advanced level physics, electronic means a transistor is by connecting two P semiconductors into an N semiconductor, a PNP transistor can be constructed. When connecting two N semiconductors to a P semiconductor, that is a NPN transistor. That is not advanced level up. And circuit symbol of a transistor is this. That is arts. Any matter can teach like that. The internal structure should be taught like this. And these two diodes completely behave in completely different ways, dear. If I name this diode as diode D1, and the diode D2, they behave in a very completely different ways. In the examination, they ask, how do you bias D1 diode? How do you bias D2 diodes? If you know only PNP and PN names, you cannot answer such questions, right? So therefore, it's very important to learn electronic lesson from a teacher who has really studied electronic lesson in university level. Otherwise, you can't. He can't teach. He can't teach means you can't learn, right? Draw both circuits. So there is a, even for the circuit symbol, there's a huge story behind the circuit symbol. The circuit symbol of a transistor has a huge story, and there's a huge description should be given for this D1 diode and this D2 diode. For D1 and D2 diodes, a huge description should be given. Otherwise, you will not be able to do the electronic question asked in the examination. Okay, dear. Lamai, Pulai girl.
Okay, sir.
When I say Pulla and Pullai girl, students laugh at me. Didn't I pronounce it the proper way? Shadil, didn't I pronounce it in a proper way?
Yes, sir.
Correct me?
Yes, sir.
Yeah. Okay, draw the circuit, and we need more time to discuss this circuit symbol and other things. But I think I have given you the basic idea. And next time, I think I'll be able to go to proper descriptions and proper descriptions and past paper questions, even from electronic lesson, right? Bridge circuits will be discussed at the end of the lesson, at the end of everything.